Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Abudewa Sos Ugobela Wemets. And without any further ado, let's just get right down to the lesson. Okay, so we have momentum and impulse, and as we can see, it's a full video lesson. So we'll be going through everything that you need to know about momentum and impulse, and also having to go through those exam type questions so that you build that confidence in order to ace your test and ace your exams. Okay, so we have our lesson objectives. It says by the end of the lesson, we should know all the necessary terminology under momentum and impulse. We should be able to know all the formulae that will be used, and then also the different cases of collision. And then we'll have to know how to use the impulse momentum theorem and the Newton's second law in terms of momentum in order to calculate the impulse and the net force. And also we must be able to know the difference between the elastic and inelastic collision. And then lastly, we're going to have our exam practice questions. So, okay, let's get right down to business. We have a terminology. The first term that we see there is momentum. It says momentum is the product of the object's mass and its velocity. So this is how you are expected to define this term in your exam, right? So impulse also is the product of the net force and the time taken for the net force to act on the object, right? So make sure that you know this definitions verbatim, the way they are. That's how you should write them. So principle of conservation of linear momentum states that the total linear momentum in an isolated system is conserved or it remains constant. Then we have isolated system is a system for which the net external force is equal to zero. Elastic collision is a collision for which both the total linear momentum and kinetic energy is conserved, right? Then we have inelastic collision. We say this is a collision for which the total linear momentum is conserved, but kinetic energy is not conserved. Then we have the impulse momentum theorem states that the impulse of an object is equal to its change in momentum. Then lastly, we have the Newton's second law in terms of momentum states that the net force acting on an object is equal to the rate of change in momentum in the direction of the net force. So I hope you have your notebook there and then you have written down these definitions, right? So make sure that when you watch this video, you have your notebook with you and then be proactive. Do not just watch the video, but then have that notebook so that you can note the things that you need to note and also try to do some calculations that we'll be doing there. Okay, so let's proceed. We have a formulae. So the formulas that we would have to use under this topic here. Firstly, it's the formula for momentum, which goes P is equals to M times V. And then secondly, it will be the change in momentum, which is almost similar to that. But then here, you have to consider that this will be mass multiplied by the change in velocity, which if you can break it down, you can say mass and then bracket V finally minus V initial, right? So you need to really note that definition right there. Right, so we have this this formula here saying definition, it's a formula. So know all these formulas here. And then the third one, we will have the impulse momentum theorem, which in most of the cases you find it like this: F net delta T is equals to change in P. So this is the impulse momentum theorem. This is another formula that you'll have to note right there. And then also you must know that the impulse, as we have defined, we said the impulse is the product of the net force and the time. So impulse is that F net delta T. So this part here is impulse, right? And then this is change in momentum. Hence, the impulse momentum theorem states that the impulse is equals to the object's change in momentum. So this is change in momentum. And then we can have it like that. So this is also another formula that you'd have to know there. And then also with this formula here, they can play it around. Sometimes you can have it in this format. So other documents have it as change in P over change in T. So this will say it is a momentum in, this is a Newton's second law in terms of momentum, right? Newton's second law in terms of momentum. So it's just simply manipulating this to make your F net the subject of the formula. So most of the cases, if they just say they want you to calculate the average net force, this is how you can write it. And then if they say they want you to calculate the impulse, this is how you can have those formulas, right? Okay, and then we also have another one. It's EK. EK is equals to half mv squared. So kinetic energy, right? So that's EK is kinetic energy. And then that's how we're going to have it. And then we'll also have the principle, the formula for principle of conservation of linear momentum, which in most of the cases we have sum of momentum initially is equals to sum of momentum finally, right? Now with this one, this is where we have the different cases of collision, right? So in most of the cases, you will just have momentum initially for object A plus momentum initially for object B is equals to momentum finally for object A plus momentum finally for object B, right? So we're still going to speak more about this one here. But then as we can see here, with the formulas, you also need to understand the keys there and also what we have here, the symbols, the key or the symbols, what they mean. So P is for momentum. P is for momentum. And as we know with physical sciences, if you don't indicate the SI unit, you get penalized. So you need to know that momentum is given in kg meters per second. Then we have mass, M is for mass, and then your mass, always note that it is given in kilograms. This is very important for you to note. If we are given in grams, then you need to always remember that we need to convert to kilograms. So if we are given grams and then we need to convert to kilograms, please note that we will need to divide by 1,000, right? It's very important to note because in most of the cases, you'll find that the mass is given in grams and then learners just take it exactly as it is and then put it like that. But then you always have to remember, if the mass is given in grams in physics, which is your paper one, you need to always convert to kilograms by dividing by 1,000. Right. And then we have V. V is for velocity. V is for velocity, and your velocity is given in meters per second, right? So make sure that with your SI unit, you always have them under control. Then we have your F net, which is obviously the net force. And then we know anything that is a force is given as newtons, right? And then, of course, we have our delta T, which is the time. And then time is always given in seconds. It is always very important to note again here, if your time is given in minutes, then you need to understand that converting minutes to seconds, you'd have to divide by 60 because 1 minute is equivalent to 60 seconds. So this is also another thing that you'd have to note there. And then with your change in P is simply the change in momentum, right? So there's a difference. If you only see P, it's momentum, but if it's change in P, it is called the change in momentum. Then it is still the same SI unit. It's a kg meters per second, right? It is still kg meters per second. Then we have F net delta T as a combination. That's obviously your impulse. And then your impulse is given with the SI unit Newton second, right? Now you can see this comes from F net being in newtons and then your delta T being in seconds. So we say it's Newton second. It's not Newton per second, it's Newton second, right? And then lastly, we have the EK. So EK is obviously the kinetic energy. So kinetic energy, and then with your kinetic energy, always note that it is given in joules, right? It is energy. Then, okay, so this is all that we have. These are all the formulas that we will be using when it comes to tackling our questions, right? So let's proceed to the next section of the lesson. Okay, so we now have the cases of collision, right? So cases of collision are this. So number one case of collision is that you can find that objects move separately before collision and then continue moving separately after collision. So when we are speaking about momentum, we are mostly speaking about the collisions, right? So what happens with the momentum, what happens with the kinetic energy, before the collision, during the collision, and after the collision. So obviously we have different cases in which collisions can occur. You can have a collision whereby objects were moving just separately, and then before collision, then after they collide, they still bounce back, and then they still move separately, or maybe even if they're going in the same direction, but they move separately. So there's a certain calculation that we need to know in terms of whether if a case is like that. So basically, when you are given a question paper in an exam, what you mostly need to check is which case is it? Is it case 1? Is it case 2, 3, or 4? Then question 4 here, we are given an example of such a case here. They say ball P of mass 0.16 kg. So this is what you do whenever you are looking at questions here. You always have to make sure that you highlight the data, right? So as we can see, we are given our mass in kgs, which is there is no problem with that. It is in the desired SI unit. Moving east, so this is the direction, moving east at a speed of 10 meters per second, collides head on with another ball of mass 0.2 kg. So this is the mass of another object moving west at a speed of 15 meters per second. After the collision, ball P moves west at a speed of 5 meters per second, as shown in the diagram below. And they say ignore the effects of friction and the rotational effects of the balls, right? So we are given this activity here, and then we are supposed to answer these questions under this case, whereby objects are moving separately before collision and they still continue to move separately after collision. As we can see here, we are given a diagrammatic representation. So we are given ball P and ball Q, which, as we can see, that moving with different velocities, also in different directions, and they're moving separately. After collision, we are told that ball P supposedly bounces off from ball Q here and then goes in that direction. Then we are given ball Q here, so which we can see from here that it is obviously going in its own direction separately, since these two objects are not combined. Then 4.1 says define the term momentum in words. As we saw with the definitions, we said momentum is what? Momentum is the product of the object's mass and its velocity, right? So this is the definition right there, the product of the object mass and its velocity. So as we can see, definition is a free 2 mark. Then 4.2 says calculate the velocity of ball Q after the collision, right? In a case like this, you have to understand applying the principle of conservation of linear momentum. This is how we do it. We say sum of momentum initially is equals to sum of momentum final. Now with the cardinal points, we know that east here will be representing the positive direction and west here will be representing the negative direction. So we can say here we are taking east as positive. Right. And then now, because these two objects will be moving separately, we know now it's just a matter of saying the sum of momentum initially of a ball, let's say ball P, plus the sum of moment, plus the momentum. So it's the momentum of ball P plus the momentum of ball Q initially is equals to the final momentum of ball P plus final momentum of ball Q. Now, obviously, we have seen the formula for momentum is P is equals to M times V. So this is exactly what we're going to do here. We're going to break this one down to say now we have M1, V1, plus M2 V2. Now let's say M1 V1 will be for P, and then M2 V2 will be for Q, and then is equals to M1 V1 plus M2 V2. Why are we doing this? It's because these objects are separate, right? Then our mass, as we can see here, we just simply take it from the statement. Mass 1 is 0.16 kg, and then it is moving east, meaning this is the positive direction. So this is how you tackle questions in an exam. Make sure that you always highlight your data. Then the velocity is 10, and then we have mass 2, it is 0.2 kg, and then the velocity is west. Now, if it's west, that means it's a negative direction. So how am I supposed to substitute this 15? I'm supposed to substitute it as a negative. So we have negative 15. So note that whenever it says west, then it's the negative direction. You simply take the value and substitute it as a negative. Then mass 1 after the collision, obviously, we assume that there is no loss of mass during the collision, as with most of the cases. But now P is moving west. So west, this is the negative direction. So at a speed of 5 meters per second. So we're going to have negative 5, right? And then plus our mass 2 is 0.2. But then remember, what we are supposed to calculate is the velocity of ball Q after the collision. After the collision, that's for final, right? And then initially it's before the collision. So we have V2 final, right? Then obviously, from here on, you need the aid of your calculator, which you're going to just press everything that's on your left-hand side. That's 0.16 multiplied by 10 plus 0.2 multiplied by negative 15, right? So this side up, we are going to have negative 1.4. And then equal to, we have 0.16 times negative 5, and then which will give us negative 0.8, then plus 0.2 V2 final. Now, obviously, knowing our maths, we have to take this one and transpose it over to this side. We have negative 1.4, and then plus 0.8 is equals to 0.2 V2F, right? Now, we're going to have negative 1.4 plus 0.8, which will give us a negative 0.6, and then is equals to 0.2 V2F. And then dividing both sides by 0.2, then we can conclude that therefore our V2F will be equals to, punch that into your calculator, that's negative 3 meters per second, right? But obviously you're not going to leave it as a negative here, because the negative is telling us about something in physical sciences. So the negative in physical sciences usually indicates the direction. So therefore we have to come here and say, therefore our V2F is equals to 3 meters per second. To which direction? To the west, right? So it is to west. And then now we can tell from that what happened to ball Q is that it was slowed down, right? So what happened to that is that it was slowed down. It was moving at a velocity of 15 meters per second, and then now it is slowed down and then still moving in the western direction, but then it has a lower velocity. So okay, that's basically what we get from all this. So as we can see, this is how we tackle the situation whereby we have objects moving separately before collision, and they still move separately after collision. So this is our case 1. Okay, so now when we go to 4.2.2, it says magnitude of the impulse on ball P during the collision. Now, as we can see, magnitude of the what? Of the impulse, right? And then we did mention for 4.2.2, we did mention that impulse is equals to F net and then multiplied by delta T. But throughout all the statements here, we've highlighted the data, and then we saw with the data here for ball P, there is nothing to do with F net and delta T. We have not been given the net force. We have not been given the delta time. Now the question is, how are we supposed to calculate the impulse if we don't have F net and we also don't have delta t. Now, obviously, worry not, because now we do know about the impulse momentum theorem. The impulse momentum theorem states that the impulse can be equated to the change in momentum. So in other words, in conclusion here, we can also calculate the impulse simply just by calculating the change in momentum. So this is something that you really, really need to note here and be on this one. If you are trying to calculate the impulse and then you don't have the net force and also the delta t, your change in time, you can also calculate the impulse simply by calculating the change in momentum of the object, right? So meaning, in other words, to calculate the impulse now, I will just say M and then VF minus VI. Right. Now, what is my mass for ball P? That's as 0.16 kg. So note that they're saying on ball P. So I'm using information on ball P only. So I have 0.16. Then the final velocity was 5 meters per second, but then it was due west. So I need to substitute it as a negative. So negative 5. And then initially it was moving at a speed of 10 meters per second. So minus 10 like this. And then obviously I need to punch all of this into my calculator. I have that, and then minus 10, and then this is going to be negative 2.4 kg meters per second, right? But then I need to remember that what I'm trying to calculate is the impulse. So from here, I need to then conclude, therefore, impulse will be equals to what? 2.4 Newton second, right? So the reason I have kg meters per second is because I was calculating change in momentum. Now that I've got the change in momentum, I now say, therefore, the impulse is 2.4 Newton per second, but then the negative here, it means what? West, right? So I have 2.4 Newton second west as the impulse of ball P, and then also be careful of the SI unit. Okay, so this is basically how we would tackle this question. So we understand case number 1. This is how we are supposed to calculate it. So the main focus here was on 4.2.1, right? Then, okay, let's proceed. Now, we have case 2. It says objects move separately before collision and move together as a unit after collision. So as a unit, it means now it is a system, right? A system of trolleys, as we can see right there. Now let's have our statement. It says trolley A of mass 7.2 kg. So we know the deal. Once we are given the data, we need to just highlight it. Moves to the right. So this time around, we are not given cardinal points. Moves to the right at 0.4 meters per second in a straight line on a horizontal floor. It collides with a stationary trolley. Now, it is very important that I highlight the word stationary, because I know that stationary in physics simply tells me that the velocity is equal to 0 meters per second. And then trolley B of mass 5.3 kg. Now, after the collision, the trolleys lock together. Note that they do what? They lock together and move to the right as a unit. So they move together as a unit, as shown in the diagram below. Ignore any frictional effect. Then before collision, we have 7.2 kg A and then 5.3 kg. So in most of the cases, you are even given a diagrammatic representation of whatever that you are dealing with. Now 4.1 says, state the principle of conservation of linear momentum in width. Now as we saw with the definitions, the terminology, we already know principle of conservation of linear momentum states that in an isolated system, the total linear momentum is conserved, right? So that's basically how we have our definition. States that in an isolated system, the total linear momentum is conserved. Right. Then 4.2.1, which is the main focus of this case, the velocity of the trolley immediately after the collision. Now, the velocity of the trolleys. Why do they say the velocity of the trolleys? Remember, if objects lock together, that means they will share the same velocity. They will share the same velocity. When objects are moving together as a unit, they share the same velocity, right? It's a similar case with you inside a car that is moving at 100 meters per second. As much as you are seated in that car being a passenger and the car is driving at 100 meters per second, also you as the passenger, you are moving at 100 meters per second along with the car. Right, so now for 4.2.1, we are going to say, let's have our sum of momentum. Sum of momentum initially is equals to sum of momentum final. Now, because initially they are separate, we are going to have M1 V1 plus M2 V2. Now we understand 1 for trolley A and then 2 for trolley B. But then what happens finally? Finally, they now move together as a unit. So now the way I'm going to have this formula is now going to be different. I'm going to have M1 plus M2 sharing the same final velocity. So I have to combine the masses of these two and then make them have only one velocity. So it's very important to note that if we have this case, now this is how you are supposed to have your formula. Right. Now from here, this is how you deal with this question. What is mass 1? As we can see, it's 7.2. And then the velocity, that's 0.4. Right. And then from here, we have mass 2, which is your 5.3. But then they said trolley B was initially stationary. Then this is 0. And then that means 7.2 plus 5.3. And then the velocity that we are trying to calculate is VF, which is the velocity after the collision. So note that this is before the collision for initially, and this is after the collision for final, right? So that means we're going to have 7.2 multiplied by 0.4. Obviously, when we multiply, this is going to be 0. So we might just as well leave it like that. So we have 2.88, and then is equals to add this one up, 7.2 plus 5.3. That's equal to 12.5, and then VF. Now, obviously, when we divide both sides by 12.5, 12.5. So let's note here that we are taking right as positive. So we are taking right as positive. Then we have 2.88 divided by 12.5. This is going to give us VF is equals to, so I'm just going to round off to 2 decimal places. It's 0.23 meters per second, right? So if I only just round off to 2 decimal places, I have it like that. So basically, that's how you were supposed to approach this question right there. So this is another case, a case whereby objects were moving separately before collision, and then they moved together as a unit after the collision. Then again here, we have a question on calculating the average net force. So this time around, they're not asking us to calculate the impulse. We are calculating the average net force exerted by trolley A on trolley B. So this is trolley A on trolley B. We are mostly focused on the one that is experiencing the force, right? So on trolley B, during the collision, if the collision time is 0.02 seconds. So meaning here from this two, which information are we going to use? Are we going to use the information of A or going to use the information of B? We are going to use the information of B. The correct answer is we are going to use the information on B, because when we calculate the net force, we are calculating based on the object that is experiencing that net force, right? Now, do not be shocked by this, right? Average. They can say calculate the net force. They can say calculate the average net force. That is one and the same thing. It doesn't mean you have to calculate differently if it is just net force or if it is just average net force. In most of the cases, they will say average net force. But even if they say just calculate the net force, that is still one and the same thing. Okay, so now how are we supposed to calculate that? Remember, we do have the formula for that. It goes F net delta T is equals to change in P, which I did mention that when it comes to calculating the F net, you can also just simply write it like this, right? Which is much more straightforward because you make your F net the subject of the formula. So we're just going to go F net is equals to change in P over change in T. Now, obviously, we have to break down this, right? So this is M and then bracket V finally minus V initially over delta T. Now, what is the mass? Remember, we are going to base it on Trolley B. So with Trolley B, the mass of Trolley B is 5.3, right? And then the final velocity, we did calculate, remember? Previously, we calculated that the final velocity here is 0.3 meters per second. Now, what does it mean? It means the final velocity of Trolley A is 0.23 meters per second. And also the final velocity of Trolley B is 0.23 meters per second. Why? Because we said once they move together as a unit, they will share the same velocity. In other words, they will have the same velocity. Even if you were to separate them now, they have the same velocity. Then this is 0.23 minus the initial velocity is 0. And then they said the time of contact was 0.02. So that's the collision time. So 0.02. Then obviously all you have to simply do is punch all of that into your calculator. So umshinwe ibalo. Then we have 60.95 newtons, right? Newtons. And then since we have it as a positive, we have to say right. So that's basically how you were supposed to have that. Okay. And then also with this velocity that we found in 4.2.1, we also need to include the direction it's right because it came out as a positive. Also, do not forget to mention the direction, especially since we are working with those velocity and net force. We know those are vectors and vectors have both magnitude and direction. Okay, so that's another case. Let's have a look at yet another one. So case number 3 says we have object falls vertically onto a horizontally moving object, right? So this is also another case that you can encounter in an exam. The example is a trolley of mass 3 kg moves at 4 meters per second west. So let's have that. 4 meters per second west along a frictionless horizontal path. A brick of 1 kg, so the 3 kg was the mass of that, drops vertically into it. So let's note this. It drops vertically into it. I will explain why I highlighted that. So it drops vertically onto it. So let's have it with a different color so that I don't forget to explain it. Then, okay, now the brick lands on the trolley at a vertical velocity of 0.5 meters per second. So I'm also going to shade this in green and then calculate the velocity of the brick and trolley system after the collision. Calculate the velocity of the brick and trolley system. So we can see now this is similar to case number 2 that we just encountered right now, right? Because as we can see, the objects are moving separately. Then after the collision, they will move together as a unit. So this is still a similar case, but then it's a bit special in what I will have to explain here, right? So we have sum of momentum initially is equals to sum of momentum final. Then of course we have M1 V1 plus M2 V2, which will give us M1 plus M2, and then they will share the same final velocity as they will be moving together as a system, as a system or a unit, right? Okay, now, once we have that, let's understand this. If an object is dropping vertically here on a horizontally moving object, now we have to note that it does not have any velocity in terms of its horizontal movement. So this one, if we are to consider its horizontal velocity, if we are to consider the horizontal velocity of this brick, it is 0 meters per second, right? And then this is basically what we are looking at. Remember, when we are dealing with these questions here, especially if we have an object that is moving horizontally, we are focused on a linear momentum, which in most of the cases, that's the momentum of something that is moving in just one dimension. So the dimension that we are focused on here is the horizontal one. So meaning that if we have to check on the vertical movement of things here, we have to discard this velocity here and only consider its horizontal velocity. So this here, we understand it will be dropping onto this brick here, or this trolley. This brick will be dropping onto this trolley with a velocity of 0.5 meters per second. But the problem is that 0.5 meters per second is the vertical velocity. And here we are to only consider the horizontal velocity because the object that it falls onto is moving horizontally. So in that case, we have to consider that its horizontal velocity is 0 meters per second. So now when we substitute here, we are going to say mass 1, yes, it is 3 kg, and then velocity, it is 4 meters per second west. Remember, considering that we are always taking our east as positive, then that means the western direction will have to be indicated as negative. And then plus mass 2, we understand that it is 1 kg, but then when it comes to this velocity, I'm not going to substitute the 0.5, but then I'm going to substitute 0 because we are saying we are considering the horizontal velocity, which is 0. It is not moving horizontally as it is still dropping down to the trolley. And then we have mass 1, it is 3, and then mass 2, it's 1. So what we are trying to calculate is the final velocity here. Now, obviously, this will give us 0, and then here we'll have negative 12, then 3 plus 1, this is 4, and then VF. Now, if we divide both sides by 4, then we know that our VF will have to be negative 3 meters per second, right? And since it's negative, we know that it indicates west, so therefore we'll say VF is 3 meters per second west, right? West. And then that's basically how you calculate that. So understand that this situation can be a bit tricky when you see it in an exam, but then always remember, if there's anything falling vertically upward, assume that its velocity is 0, even if you are given its vertical velocity, because we are only considering the horizontal velocity. Okay, now let's move to the last case. So we have case number 4. Right. So case number 4 says 2 objects moving as a unit or stationary and joined together. So 2 objects moving as a unit or they are stationary and joined together will separate during collision, right? So this is more like a divorce, right? So you were together with your partner and then now you are moving separately after the divorce, right? Then question 4 says 2 trolleys A of mass 1 kg and B of mass 2 kg are held stationary on a smooth horizontal surface with a compressed spring between them, as shown in the diagram below. The spring is released and falls to the ground. Trolley A moves to the right at a constant velocity of 5 meters per second and collides with the wall. So, okay, let's highlight the important information. So we have what? The masses. So trolley A of mass 1 kg and then trolley B of mass 2 kg are held stationary. On a smooth horizontal surface with a compressed spring between them, as shown in the diagram. The spring is released and falls to the ground. Trolley A moves to the right at a constant velocity of 5 meters per second and collides with a wall. Assume that it is an isolated system. So also this is another way to say ignore the effect of friction or ignore any rotational effects of the wheels. And then 4.1 says define an isolated system. Now, as we saw from the definitions, how do we define isolated system? We say this is a system for which the net external force is equal to 0. right? So this is a system for which the net external force is equal to 0. Then 4.2 says calculate the velocity of trolley B immediately after the spring is released, right? Calculate the velocity of the velocity of trolley B immediately after the spring is released. So this is how we're going to tackle that question there. We are going to say sum of momentum initially is equals to sum of momentum finally, right? And then check with this case, it is just a vice v of the case that we had in case number 2 and case number 3. So this time around, we start with the 2 in combination, and then they share the initial velocity. Then after that, they separate m1 v1 plus m2 v2, right? So this is how we have that. So if you can check, it is the reverse of case 2 and case 3. Now, this is how we tackle that one. We are going to say mass A is 1 kg and mass of B is 2 kg, and they share the same velocity, which is stationary velocity 0, right? And then mass 1 is 1, and then they say the spring is released and trolley A moves to the right at a constant velocity of 5 meters per second. So that's 5, and then plus, so here we are going to say we are taking right as positive, and then here it's 2, so we are trying to calculate the velocity of B, right? And then this is 0 obviously, and then 1 times 5 is 5, then plus 2v2, so we can take the 5 over to this side or take this over to this side. We have negative 2v2 is equals to 5, right? Divide by negative 2, divide by negative 2, then our V2 is 5 divided by negative 2, which will give us a negative 2.5 meters per second. And then since it's negative, we know that it indicates to the left. So V2 is equals to 2.5 meters per second, and then to the left. Note that when we are given in terms of cardinal points east-west, then we are supposed to also conclude using east and west. But then if we are given that it is going to the left or the right, then we must conclude using left and right. So always keep to the terminology of the examiner there. If the examiner says left, right, then that's how you do it. If the examiner says east and west, then that's how you also conclude that, right? So do not change the terminology of the examiner, right? So basically that's what we have. These are all the cases that we have under collisions, so make sure that you know them properly. Okay, so now let's move to another section of the lesson. Now we are given the difference between the elastic and the inelastic collision. So with the elastic collision, this is what we must know. The total linear momentum is conserved, which is also the same with an inelastic collision. The total linear momentum is conserved. So these are the two similarities. Then sum of the momentum before is equal to sum of momentum after the collision, which obviously will be the same. Sum of momentum before is equal to sum of momentum after the collision, right? But then the differences lies in this two again. Then kinetic energy is conserved, but then here kinetic energy is not conserved if it's inelastic. Now with inelastic collision, these are the collisions that we mostly see in real life. So most of our real life collisions are inelastic collisions, right? Because obviously we say that the kinetic energy is not conserved. So if there is a crash or an accident, then we know that that energy will be converted to some form of energy. So when you hear that sound, when there is a crash, that means there is a certain kinetic energy that is being converted to sound energy. And then after the crash, when you have to touch the bumper or the body of the vehicle, you will feel that it is hot. So some of the kinetic energy is being converted to heat energy, right? So remember, energy cannot be destroyed nor created, but can be changed from one form to another, right? So there's a transfer of energy in an inelastic collision, which is mostly what we see in real life. Now, with elastic collisions, they are very minimal in real life. Now, the only way you can create an elastic collision is to have a perfectly vacuumed place, right? Whereby you know that the kinetic energy will be conserved and will not be lost, right? So, okay, sum of kinetic energy before is equal to sum of kinetic energy after the collision with an elastic collision, but then here sum of kinetic energy before will not be equal to sum of kinetic energy after the collision. So basically here in a mathematical form, we have the fact that sum of momentum initially is equals to sum of momentum final. Also here, sum of momentum initially is equals to sum of momentum finally. So the sigma here reads as sum of. You know that from maths. And then sum of kinetic energy initially is equal to sum of kinetic energy final. But with this one here, sum of kinetic energy initially is not equal to sum of kinetic energy finally, right? So these are the things that you have to consider under elastic and inelastic collisions. Now, obviously, there is that question. Most of the time, you find that it is 5 marks, where you need to prove whether a certain collision is elastic or inelastic. So before the end of the video, we will tackle such a question so that you build the confidence to tackle it if you see it in your exam, right? Then let's have reducing the impact of the net force. So when there is a collision or an accident, we know that there can be fatal accidents or fatal injuries that might lead to deaths sometimes. So to reduce that, obviously scientists came up with a plan, and then they said there are safety features that we can put into vehicles so that it can prevent fatal injuries to the driver and also to the passengers. Right. So the safety features include your safety belts, your airbags, your flexible bumpers. So basically what these features do is that they reduce the impact of the net force by increasing the time taken for the net force to act on an object over the same change in momentum. So thanks to all those safety belts, airbags, and flexible bumpers, now the impact of those accidents or collisions are now not that very deadly, right? But then before these safety features were invented, we know that a collision can simply lead to death. Okay, so now let's proceed. Now, question 4 says trolley X of mass 1.2 kg travels at 8 meters per second east. So at this time around, we are trying to practice exam questions to solidify our knowledge and then also build confidence, right? So trolley X of mass 1.2 kg. So let's highlight. So this is the method that I want you to develop, guys. Whenever you are working with these questions, always collect your data, right? Always make sure that your paper is colorful. Then a trolley X of mass 1.2 kg travels 8 meters per second east and collides with trolley Y of mass 0.5 kg, which is initially at rest. At rest means that it is stationary. Ignore all frictional effects. It is an isolated system. The velocity time graph below shows the velocity of trolley X before, during, and after the collision with trolley Y. Note that it shows the velocity of trolley X. The velocity of trolley X, as we can see with the title here, this is the velocity time graph for trolley X. So everything that you are seeing here only relates to trolley X, right? So it says it's showing before, during, and after the collision. So let's check that. This is before the collision, this is during the collision, and this is after the collision, right? Now, 4.1 says, state the principle of conservation of linear momentum. We already know principle of conservation of linear momentum states that in an isolated system, the total linear momentum is conserved. The total linear momentum is conserved. Now, 4.2.1 says velocity of trolley y immediately after the collision. So we want the velocity of trolley y. Now, obviously, from reading this statement here, we can see that we are not told that trolley x and trolley y combine after the collision, right? So if there is no mention of that, the assumption is that the objects are moving separately after the collision. If the objects are moving together as a unit, it's either they will tell you on the statement or they will try to show you with a diagrammatic representation. But if there is no mention of the trolleys or any objects moving together after the collision, then always assume that it is case number 1, right? So we have for our 4.2.1, this is how we're going to have it. So we're going to have sum of momentum initially is equals to sum of momentum final. Now, as we can see, they used east-west. So this is our reference. We're going to say east as positive. So this is going to be M1 V1 plus M2 V2 is equals to M1 V1 plus M2 V2. Now, what is mass 1? So we're going to take M1 as trolley X. So M1 as trolley X and then M2 as trolley Y. So M1 is the mass of trolley X is 1.2. And then the velocity is 8, which is before the collision. Remember, initially that's before the collision. So that's 8. And then mass 2, that's trolley Y, it is what? 0.5. But then we are told that it is initially at rest. So at rest means the velocity initially was 0. And then M1, it's 1.2. But then after the collision, remember for final, it's after. So after the collision, we find that the velocity is what? It is 4. So this is how you read the graph. And then it's 4. Then mass 2 is 0.5. And then this is what we are trying to calculate, V2. Now, obviously, simply grab your calculator. This is going to give you 0. So we have 1.2 multiplied by 8. So which is going to be 9.6. Now, 1.2 multiplied by 4 will give us 4.8. Then plus 0.5 and then V2. Now, you're going to have to take this and transpose it over to the side. 9.6 minus 4.8 is equals to 0.5 V2. So we have 9.6 minus 4.8 is equals to 4.8 and then is equals to 0.5 V2. If we divide both sides by 0.5, then our V2 will be what? Will be the 9.6. So 9.6 meters per second. And then to which direction? Since it came out as a positive, we are going to say to the eastern direction, east. And then that's basically how we would calculate and get that 4 marks right there. Okay, nice. Then for 4.2.2, we are given average net force the trolley X exerts on trolley Y during the collision. Average net force the trolley X exerts. So again here, let's check. Average net force the trolley X exerts on. Remember, when we are calculating the average net force, we simply calculate it based on the object that is experiencing the net force. So average the net force the trolley X exerts on trolley Y during the collision, meaning I'm using the information for trolley Y, right? So, okay, now having to calculate, this is 4.2.2. I will have a F net delta T is equals to change in P, which I did mention that you can then manipulate to say F net, subject of the formula, change in P over delta T. Then our change in P is your mass bracket VF minus V initially over delta T. Now, what is your mass here? Your mass for Trolley Y, it is 0.5 kg, right? And then your final velocity is the one that we calculated, 9.6. And then initial velocity is 0. And then over delta T. So now, how are you going to find the delta T? This is the collision time, right? So how long did the collision last? Remember, this is during the collision. So that means the time of the collision is in between here. So you don't use 20.1, you don't use 20.2, but rather you have to find the difference between the times here. So in between here, this is the collision time. This is the collision time. Then you are supposed to say 20.2 minus 20.1, right? So 20.2 minus 20.1, that means you are going to get 0.1. So here you substitute 0.1, right? Then, okay, you have 0.5 bracket 9.6 minus 0, and then divided by 0.1. So we are going to get 48 newtons. And then since it's positive, it's 48 newton east, right? So that means Trolley Y is experiencing a force of 48 newton to the eastern direction as a result of Trolley X. So this is due to Trolley X. Now, you could still get the same value from calculating using Trolley Y, but then you would have to be very careful with your conclusion, right? So if you were to maybe calculate using Trolley X, right? If you were to calculate using Trolley X, this is how you'd calculate it. So still the same, okay? You'd say the mass is obviously your 1.2, and then your VF is your 9.6, your VI, we are given, no, using the wrong one. So the final velocity is 4. For Trolley X, the initial is 8, and then over 0.1. Since obviously they will have the same collision time. Remember, they were colliding together. Then when you punch that into your calculator, you get negative 48 newton, which, as you can see here, it's negative because this indicates the net force that Trolley Y is actually exerting on Trolley X. Now, why are they equal? This is based on Newton's third law, right? The reason they are equal is based on Newton's third law. Now, what does Newton's third law state? It states that when object A exerts a force on object B will simultaneously exert a force of the same magnitude, but in an opposite direction. As you can see here, this is a Trolley X on Trolley Y. And then this here, this is Trolley Y on Trolley X, right? So note that they will have the same magnitude but different directions. Obviously, when you conclude on this one, you are supposed to say 48 Newton west, right? So this is the net force that Trolley Y exerts on Trolley X. But since here we are being asked the one that Trolley X exerts on Trolley Y, you then have to conclude that actually Trolley X on Trolley Y would have to be 48 Newton east. So that would be your conclusion if ever you use this one. Because remember, you'd have to remember that this is Trolley Y on Trolley X. So to find Trolley X on Trolley Y, then it means it's the opposite direction. Okay, so note that, which is it is much simpler and easier to calculate based on what is experiencing the net force. Now, 4.3, this is our main question here. Is this collision elastic or inelastic? And then how many marks? 5 marks. So I did mention that to say that there will be a calculation which is asking you about whether a collision is elastic or inelastic, and then you'd have to provide a suitable calculation for that. Now for this one, there is one thing that you need to note, right? You would need to calculate the sum of kinetic energy before the collision, and then the sum of kinetic energy after the collision, but then you have to calculate them separately, not side by side. Note that. Do not calculate side by side. You have to calculate separately. Then this is 4.3. So what do I mean by that? I will say, okay, before collision, I have a sum EK initially is equals to, so this will be, so let me just have it below here, half mv squared plus half mv squared, right? So I will say this is for trolley X and then this is for trolley Y. So these are the initial velocities. Mass 1.2 and then initial velocity of trolley X is the 8 right there. And then plus half, I have 0.5 here. And then initially this was 0, right? As they mentioned here, initially at rest. Now, obviously, the whole of this will give me 0. So I'm only going to do this part, 1 over 2, and then 1.2, and then 8 square, right? So I'm getting 38.4 joules. Now, after that, I have to indicate after the collision. After collision, and then again, I have sum of EK finally. Then this will be half mv squared plus half mv squared. So finally now, it's not initial, then for X and then Y. So let me indicate this is initially, and then this is half mass. Obviously, we assume there is no change in mass during the collision. Then finally, it has slowed down to 4. And then mass is 0.5. And then final velocity is the one that we calculated to be 9.6, right? Then obviously you have to punch all of that, carefully punch all of that into your calculate. And do not forget the square. A lot of learners have the mistake of just forgetting that square for the EK. So make sure that you are not part of that stat. And then here, when we calculate, we end up with 32.64 joules. And as you can see, there is a decrease in kinetic energy from before the collision to after the collision, meaning there was loss in kinetic energy. Some of the kinetic energy was converted to other forms of energy. So because these are not equal, we are going to say collision is inelastic, right? Our conclusion is that the collision is inelastic. Why? Because sum of EK initially is not equal to sum of EK finally, right? So that's our conclusion right there. Collision is inelastic because EK initial is not equal to EK final. Again, note, you are not supposed to calculate this side by side the way we do with momentum. You are supposed to calculate separately, right? So calculate before collision, calculate after collision, and then conclude. Okay, so nice. I hope that is well. Okay, now we have another question. It says, question 6, a truck of mass 5,600 kg. So now we are working with bigger objects. So do not have the fear of big numbers. I don't know what they call that, but then whatever the fear is, do not have that, right? Whatever that phobia is, do not have it when it comes to dealing with physical sciences or maths. Then collides with a stationary car, of mass 1,800 kg. The collision lasted 0.59 seconds. So this is the collision time. After the collision, the truck and the car are coupled. So we couple, that means they are moving together as a unit. Ketile, and move together eastwards, right? So coupled and move together eastwards, right? So that's how we have it. Okay, then 6.1, state the principle of conservation of linear momentum, which we've been stating it for a while now. It states, now, this is what you do, guys, whenever you are practicing exam type questions or your previous exam questions, make sure that you repeatedly write those definitions. Do not wait up until you are writing the day after in order to practice your definitions, because it's simply just gonna eat on the time that you could be doing calculations and all that. So just make sure that you memorize the definitions by writing them as many times as possible whenever you are practicing. Even if you are to see the same definition 3 or 4 times, just write it whenever it appears. So that actually ensures that you remember the definition when you have to write. Then states that in an isolated system, the total linear momentum is conserved. The total linear momentum is conserved, or it remains constant. So that's the definition right there. Then 6.2.1, velocity of the track car system after the collision, meaning they're looking for the combined velocity after they're now coupled together, right? So as we can see, this is our case number 2. So objects were moving separately before collision. Then after the collision, they now move together as a unit. So that means we are supposed to have 6.2. That's a sum of momentum initially is equals to sum of momentum finally. And then we have our M1 V1 plus M2 V2 is equals to M1 plus M2 and then VF like that. Right. Now, what is mass 1? That's 5,600. Then velocity 1, we are told that it was traveling 10 meters east. So we are going to say we are taking east as positive. So that's 10 here. And then mass 2 here, we are having 1,800. And then velocity 2, remember, it collides with a stationary car. So stationary, we already understand that it means 0. Then 5,600 plus 1,800, and then this is the velocity we are calculating. Now, obviously, this part will just give us 0 because any number multiplied by 0 is 0. Now, having to deal with this is 56,000, right? And then 5,600 plus 1,800, we are going to have 7,400. And then VF. Now, obviously, dividing both sides by 7,400, our final velocity is 56,000 divided by 7,400. And then this will give us 7 point, rounding off to 2 decimal places, 57 meter per second, right? And then since it's positive, I'm going to say east. And then just like that, I have the 4 marks in the back. So you see now I have 6 marks, just as simple as that. No sweat, right? So momentum is a very, very easy topic, guys. Then 6.2.2 says force that the truck exerts on the car. Note that force that the truck exerts on the, so we are focused on the one that experiences that net force, right? On the car. So that means I'm going to use the information of the car. So 6.2.2, this is F net delta T is equals to change in P, which I'm going to manipulate to F net is equals to change in P over change in T. Then M VF minus VI over delta T. Now, what is the mass of the car? It is 1,800. Now, what is the final velocity of the car? The one that we just calculated, it's 7.57. And then minus, initially they said the car was stationary, so it's 0. Then over the contact time or the collision time was 0.59 seconds. So I'm putting 0.59. So we can see with the time we've been steadily being given in seconds. So there was no need to convert anywhere. then 7.57 minus 0. Punch all that into your calculator, umshini weibalo. Then you have 23,094 point, round off to 2 decimal places, 92 newtons. And then to which direction? It's east, right? Since it comes out as a positive, right? So obviously it's experiencing an easterly directed force due to the track, right? So obviously the track is moving to the east. It will exert an eastern force on the car. Then 6.3, if the collision lasted 3 times longer, meaning 0.59 multiplied by 3, meaning how long did it last now? Multiplied by 3, that's if it lasted 1.77 seconds. How will your answer in question 6.2.2 be influenced? Write only increase, decrease, or similar, right? Now, according to this formula here, F net is equals to change in P over change in T. We can see that the relationship between the net force and delta time would have to be inversely proportional. Now, inversely proportional means that if we are to increase the contact time or the collision time, then we are expecting the net force to decrease, right? So that means here for 6.3, our answer is just simply supposed to be what? Decrease, right? Decrease. And then to explain that, they say explain your answer in question 6.3, then we can say according to F net is equals to change in P over change in T, our F net is inversely proportional to delta T. That means an increase in the collision time, will decrease the net force. Right. That's it. According to F net is equals to change in P over delta T. We saw that these two are inversely proportional. So that means there will be an increase in collision time will decrease the net force for a constant change in momentum. Right? Which is your delta P. Right. So that's it. We have 6.5. 6.5 says, name 2 safety features that can be found in vehicles so that serious injuries can be minimized when collisions like this take place. Now, you will still remember from our notes that we did mention those safety features that are found in vehicles that minimize the serious injuries when collisions take place. So we said can be your safety belt. So safety belts, it can be the airbags, and then also the third one we said it can be your flexible bumpers, right? Flexible, but then they only need 2. So you can write any 2 from this 3. Then that's how you were just supposed to tackle that. Let's proceed. Okay, another one. So I hope you are still enjoying the lesson. Well done. If you are still here up until this point, you can hit that subscribe button. If you haven't subscribed yet, you can hit the thumbs up button if you are enjoying the lesson so far. Question 4 says a ball X of mass 10 kg is moving eastward with a velocity of 2 meters per second. It collides elastically with another ball Y of mass 2 kg, which was moving with an unknown velocity. Ziyakhala much. Moving with an unknown velocity. So mass of 10 kg, moving eastwards, velocity of 2 meters per second, collides elastically. So this is a very important keyword here. elastically. You need to remember that elastically means that both the total linear momentum and the kinetic energy, they are conserved. With another ball Y of mass 2 kg, with another ball Y of mass 2 kg. Right, which was moving with an unknown velocity, right? Unknown velocity. So we don't know that velocity. Immediately after the collision, ball X comes to rest. Ball X comes to rest. Then ball Y moves eastward with a kinetic energy. Note that we are not given the velocity now. We are given the kinetic energy of 36 joules, right? Now 4.1 says explain the meaning of elastic collision. What is elastic collision? We say this is a collision where both the total linear momentum and kinetic energy is conserved. Right. So this is a collision where both the total linear momentum and kinetic energy is conserved. Right. Okay, then 4.2 says calculate velocity Vy, right? Calculate this velocity here. Okay, so as we can see here, we are given the cardinal points and also we are told about eastwards, westward, right? Then we are going to say sum of momentum initially is equals to sum of momentum final. Now, there is no mention of the object moving together as a unit or maybe being together, sticking together. So obviously we have to assume that this is case number 1. We have to assume that when they collide, they move separately. And as we can see here, obviously they say X is stationary, but then Y still has some kinetic energy, meaning it's moving separately from ball X. So this is case 1, right? Then we are going to say we are taking east as positive. So we have M1 V1 plus M2 V2, right, is equals to M1 V1 plus M2 V2, right? So, but then now here is the catch. We are looking for Vy here, which is the velocity before the collision, right? We are given this, which is not the velocity. It is what? It is actually the kinetic energy. Now, we do know that with this kind of questions, we normally have 3 given velocities. But then here we only have 2. It's this, that. Now we don't have a velocity. What are we supposed to do? Since we are given kinetic energy, this is very simple. That means we would need to first calculate the velocity finally. So EK finally first, and then this is half mvf squared. Now the EK here, from here we can calculate the final velocity because we do have the EK finally for ball Y, and then just substitute it in here. Then we have half. What is the mass of ball Y? From reading here, we are told that it is 2 kg. So we have 2 and then Vf squared. Now half of 2 is just 1. So that means we have Vf squared is equals to 36. Now obviously if you square root this, then our Vf is supposed to be what? 6 meters per second. To which direction? East. As indicated, okay, not east. Then let's check. They say it collides elastically with another ball Y of mass 2 kg, which was moving with an unknown velocity Vy, right? Vy. Okay, so here, okay, this one is east because we are shown the arrow here. Okay, I was looking at the wrong one. Okay, so we are right with east because we were calculating this one. Sorry for that. Then, okay, Vf is 6 meters per second east. So this is the velocity finally, as we indicated. Then, okay, now to substitute in here, we are simply just going to say we have our mass 1, which is 10, And then our velocity 1, 2 meters eastward. And then mass 2, it is 2, but then we don't know this velocity. That's what we are looking for. So let's say Vy. And then mass 1 here is 10, but then the velocity after, it says it's 0, right? It comes to rest. Then mass 2 is 2, and then this velocity we have calculated, and then we found 6. So that means we needed to start here. Hence, we can see it's 5 marks. Now, you need to understand one thing in physical sciences. With a 5-mark question, it means that before you calculate what you are asked for, there is a certain variable that you need to first calculate, right? So calculate one missing variable so that you can then calculate the one that you are looking for. So 10 multiplied by 2, that's 20, then plus 2 Vy, and then here this is a 0, obviously. 0 here, and then this 2 times 6 is 12, right? So we have 2 Vy is equals to 12 minus 20, and then 2 Vy is equals to negative 8. Then dividing both sides by 2, therefore our Vy will be equals to negative 4 meters per second. So as we can see with this one, they did not indicate the arrow, right? So that means they needed you to find the magnitude and also the direction, right? The magnitude and the direction. So hence they did not indicate any arrow here. So with the negative here, because we took east as positive, we're going to say therefore Vy is 4 meters per second. To which direction? West, right? West. So hence they did not indicate any arrow there. So we found both the magnitude and the velocity, the magnitude and the direction of that velocity. Okay, so 5 marks in the bag, just like that. Okay, then we proceed to 4.3. We have a statement above. It says the balls were in contact with each other for 0.1 seconds. So this is the collision time. Then during the collision, calculate the magnitude of the force. So you see right now, they did not say the average, but then we know that we are still calculating the same thing. Calculate the magnitude of the force that ball X exerts on. Remember, we are interested on the object that experiences the force on ball Y during the collision. So that means we are going to use the information for ball Y. We are going to use the information for ball Y. Then 4.3, that's your F net delta T is equals to change in P, which you need to then manipulate to F net is equals to change in P over delta T. Now this is M Vf minus Vi over delta T. So it's on ball Y. That means I'm using the information for ball Y. What is the mass here? It is 2. And then final velocity, remember we did calculate here and got 6 meters per second. And then we did calculate the Vy here and got negative 4. So note here, because it's negative, we can simply just substitute it inside here as negative and then like that, which will make this negative, negative, positive. And then this is your delta T here. It is 0.1 seconds, so 0.1. So we have 2 bracket 6 plus 4 over 0.1, which you can just punch into your calculator right away. Then 2 bracket 6 plus 4, close bracket, and then 0.1. And then this is 200. Now, it is not necessary for you to show the step. You can just simply move from here to this step here, because we do understand it became a positive as a result of the negative times negative there. Then 200 newtons, right? To which direction? Since it's positive, that means it's east. And then it does make sense because X is coming from an eastern direction, meaning it's exerting an eastward force on a ball Y. Okay, then 10 marks like that, 10 marks like that in the bag. Then, okay, let's proceed. Let's proceed. Do we have another question? Yes. Okay, so now we have question 4. It says a wooden trolley of mass 2.7 kg moves to the left with a constant velocity of 3 meters per second. So as we already know, let's highlight our data. Mass is 2.7. Direction is left, so meaning it's negative, and then with the velocity of 3 meters per second. A bullet of mass 0.03 kg is fired horizontally from the left. Now note that it's fired horizontally from the left. Now if it's fired from the left, that means it's going to the right. Note that they're not saying it is fired to the left, they're saying it's fired from the left. So meaning it is going to the right. Then towards the trolley, the bullet strikes the trolley and comes to rest inside the trolley in 0.02 seconds. The average net force exerted by the trolley on the bullet during this time is 591 Newton. Note that this is the net force. This is the net force exerted by the trolley on the bullet. The net force exerted by the trolley on the bullet. Then, okay, the bullet trolley system. The bullet trolley system combination now moves to the right. Okay, now ignore all frictional and rotational effects. 4.1 says write down the magnitude and direction of the average net force that the bullet exerts on the trolley. Note that the net force that the bullet exerts on the trolley. Now, what's different between these two statements? Here they said the net force exerted by the trolley on the bullet. Here they are looking for the net force that the bullet exerts on the trolley. Now, we do know one thing according to Newton's third law. Right. According to Newton's third law, we know that the force that the bullet exerts on the trolley will be the same magnitude as the one that the trolley exerts on the bullet. The only difference is that they will be exerted in the opposite directions. So the trolley exerts a force to the west or to the left of the diagram there, or towards the bullet. And then now the bullet will have to exert a force that is to the right, which is towards the trolley, right? But then in terms of the magnitude of the force that will be exerted, it will be the same, 591 newtons. So according to Newton's third law, we have the same magnitude of force, but in opposite directions. Right. So we have the same magnitude of force, but in opposite directions. Now we understand that the trolley is exerting a force on the bullet to the west, but then the bullet is exerting in the eastern direction or to the right. So because they've used a left and right here, we are supposed to use that. Remember, let's not change the terminology of the mark or the examiner. Then 4.1 says we are going to have 591 Newton. To which direction? Right. Because now as we can see, the bullet is moving towards the trolley and then it is being fired from the left, meaning it's going all the way to the right. So, okay, that's it. Now 4.2 says calculate the magnitude of the velocity with which the bullet strikes the trolley. Okay, so fasten your seatbelt now. It is getting pretty difficult. Then calculate the magnitude of the velocity with which the bullet strikes the trolley. So they're looking for the V initial, right? Now, we have the V initial of the trolley, which is 3 meters per second, and then it's to the left. But then here, we don't have this, the final velocity for the combination. Now, obviously, what are we looking for? We are looking for the initial velocity of the bullet, but then also we find that we don't have this. Now, in a question like this, we are already accustomed to this structure. In most of the cases, you'll find that this is about 5 marks. They were a bit stingy for giving us 4 marks. But then, okay, anyways. Now, with this type of questions, this is what you need to understand. This here is an inconvenience, right? This here is an inconvenience. I normally call it that. We are looking for this, but then we find that we don't have that. So now we have to deal with this inconvenience so that we can now directly tackle the question, which is looking for that. So in a case like this, we have to first calculate that. The VF, which is the one after the collision right there. Now, how are we supposed to calculate that? If we can check up there, we are given the net force and we are also given the collision time. Meaning if we try to calculate using the impulse momentum theorem, then we can end up with something. Now, to begin our 4.2, we need to start from F net delta T is equals to change in P. Then we say our F net. Now, the question is, am I going to use the reference as my Trolley or as the bullet? So I'm going to use what I just got from 4.1 here, which is the magnitude and direction of the average net force that the bullet exerts on the trolley. So I want the one that is experienced by the trolley, since with the trolley I have at least the initial velocity. So now the magnitude and direction that we found here was 591 newtons to the right, which means it needs to be positive if I'm taking right as positive, right? And then F net will just be positive 591. Delta T here is 0.02. And then I have M VF minus VI. Now, obviously, I need to punch this into my calculator, 591 times 0.02. And then this is giving me 11.82. Now, the mass that I'm going to use is that of the trolley, right? So it is 2.7 because I'm trying, this is the net force here. This is the net force that has been experienced by trolley, by this trolley, the wooden trolley. Then VF, that's what I'm looking for. But then what is V initial? That's the 3 right there. But then since it's going to the left, I have to substitute it as -3. So there we go. -3. Okay, so this is 11.82 is equals to 2.7, and then we have VF plus 3 negative, and negative is positive. Then I can simply divide both sides by this 2.7 there in order to get rid of it. And then 11.82 divided by 2.7, then I'm ending up with 4.378. So I'm just going to round off to at least 3 decimal places for now. And then this is VF plus 3. Now, if I take this over to that side, that's VF, it's 4.378 minus 3. Then VF supposed to be that minus 3 is 1 point. If I round off to 2 decimal places, it's now 1.38 meters per second, right? And then to which direction, since it came out as a positive, it's to the right. And then we have calculated the velocity here of the combination. So we are not done. This is not us being done with the question. Remember, we were still calculating the inconvenience. So this was the inconvenience. Now, at this point, we need to take this velocity now and go back to our formula for sum of momentum. Sum of momentum initially is equal to sum of momentum finally. Now, from this case, we can tell that this is a case whereby they were moving separately before collision, but after the collision, they now move together as a unit. So this is supposed to be M1, V1 plus M2, V2. Then after the collision, they obviously have to share the same velocity since they are moving as a unit. Now M1 here, that's the bullet 0.03. And then the initial velocity, this is what we are looking for, V1. Now others might say, but then they said the bullet strikes the trolley and comes to rest. Now the coming to rest here, it's not indicating that the velocity of the bullet is now 0, right? It is now 0 in terms of it's no longer moving, but then the whole system now is moving together. So the rest in this case means that the bullet is just embedded inside the wooden trolley. So the rest in this case means that it is embedded in the wooden trolley, but then since it's moving along together with the wooden trolley, that means now it has to take the velocity of the wooden trolley, and then now that becomes its final velocity. plus m2 here is 2.7, and then we have negative 3 is equals to 0.03 plus 2.7, and then we have VF, right? So this is 0.03 VI, and then 2.7 times negative 3 is negative 8.1 is equals to 0. So the final velocity, we did calculate this. We did calculate this. Why am I not substituting? 0.03 and then plus 2.7. And then the final velocity is the one that we calculated, 1.38. Right. So 0.03 plus 2.7, which will give us 2.73. Then multiply that by 1.38. Then it's 3.7674. And then 0.03 VI is equals to 3.7674 plus 8.1, right? Then we have 0.03 VI is equals to that plus 8.1 is 11.8674. Then we can divide both sides by 0.03. So make sure that you don't round off until the final answer. So this is 395.58 meters per second, which makes sense for a bullet. Remember, a bullet moves at a very, very high velocity. So 395.58 meters per second, that becomes the velocity with which the bullet strikes the trolley, right? So you saw how we calculated that. First, we had to calculate the combination, the velocity of the combination, and then from there on, we can then use it to calculate the initial velocity of the bullet before it strikes the trolley. Right. Then 4.3, we have the definition. We are used to having the definition as our first question. This time around, they just decided to change the structure. So principle of conservation of linear momentum, we say it states that in an isolated system, the total linear momentum is conserved, right? Or you can say it remains constant. Then 4.4 says calculate the magnitude of the velocity of the bullet-trolley combination after the collision. So they want the V finally right now. Then all we can do now is simply say, again, if we can just say 4.4 and then use the same formula. So momentum initially is equals to momentum final, right? Then we have M1 V1 plus M2 V2 is equals to M1 plus M2, and then this is VF, right? So my M1, that's the bullet, that's 0.03. Remember, I've already now calculated this velocity here. That was 395.58 meters per second. So 395.58, and then plus my mass number 2 is 2.7, and then velocity, that's negative 3. And then mass 1, that's 0.03, then plus 2.7, then VF, right? Because now we are looking for the velocity of the combination. Now we can have all that punched into our calculator. Then this is going to give us 3.7674 is equals to, adding these ones, that's 2.73, and then VF, dividing both sides by 2.73, then our VF is supposed to be what? That divided by 2.73, it's going to give us 1.38 meters per second. So it's more like we are trying to prove that the answer that we got for 4.2 here was correct, right? So this is it. 1.38 meters per second to which direction? To the right. So, okay, that's basically how we were supposed to calculate that. So, okay, we have all our marks there in the bag. So that was how many marks? 11 marks, right? So 11 marks. Okay, nice, nice, interesting. Then, okay, we have the last one here. For 9 marks, it says a 10 kg block traveling at 2 meters per second to the right. 2 meters per second to the right. Collides with a 2 kg block traveling at 4 meters per second to the left, as shown in the diagram. The collision is elastic. Now, remember with elastic, we said both the kinetic energy and the total linear momentum is conserved. Now, after the collision, the 10 kg block has a velocity of x meters per second, and the 2 kg block has a velocity of y meters per second. Explain what is meant by an elastic collision. So, what did we mention? We said an elastic collision is a collision where both the total linear momentum and kinetic energy is conserved. Right. Then 4.2 says determine the velocity of each block after the collision. Determine the velocity of each block after the collision. Right. So now let's gather our facts. So, okay, dealing with this question can be a bit tricky, but I want you to actually pay attention to this. And after you have watched this, you can comment on how you were able to calculate this if you would have a different approach. But then since I did mention that with elastic collision, we know that both kinetic energy and the total linear momentum is conserved, I will have to use the two different equations, right? So one for kinetic energy and also one for the sum of momentum, right? Now, considering that momentum is conserved, my first equation will be sum of momentum initially is equals to sum of momentum final, which from reading here, we are not told that this becomes a system. As we can see, the velocities are not the same, suggesting that they will move separately. Initially, before collision, they were moving separately. After collision, they still move separately. So this makes it case 1. Now I have M1 V1 plus M2 V2 is equals to M1 V1 plus M2 V2. Okay, now mass 1 will be the 10 kg and mass 2 will be the 2 kg. I have 10 and then it's going to the right. So let me say right as positive. Right as positive. So this is 2 and then mass number 2 will be 2, but then the velocity is 4 and then it's going to the left. So it's supposed to be indicated as a negative. Is equals to 10, but then the velocity is x. And note that we are not given the direction. So it's just x. And then plus mass 2 is 2. And then again, we are not given the direction. So it's just y. Now, if we punch all this on the left-hand side, 10 times 2 plus 2 times negative 4, all in all, we'll have 12. And then this is 10x and then plus 2y. Right. Now, considering that everything here can be divisible by 2, let me divide by 2 both sides. Right. Dividing by 2 both sides, that means I have 6 here, then I have 5x here, then I have y. Now, I can make y the subject of the formula in order to formulate an equation. So I will say y is equals to 6 minus 5x. And then I will name this equation 1. Right. Now that I have that as equation 1, I can now remember I said with elastic collision. So this whole question is based on this keyword here, elastic. So sum of momentum initial is equal to sum of momentum final. But again, we did mention that sum of EK initially is equals to sum of ek finally, right? Which means I will have half mv, half mvi squared plus half vi squared, mvi squared is equals to half mv squared plus half mvf squared. Right. Now, the reason I'm calculating side by side, it's because I already know that it's elastic. Remember, I'm not trying to prove whether it's elastic. I was told that it's elastic. So, which means it is acceptable for me to calculate side by side because I'm not trying to prove, I already know. Then this is half, and then the mass is 10. Initial velocity is 2, and then squared, do not forget. Then I have half here. And then that's 2, and then negative 4 squared, don't forget. And then half, I have 10. And then this is x squared. Then plus half, I have 2. And then this is y squared. Right. Now let me punch all this on the left-hand side on my calculator. Umshini weibalo. Umushini weibalo. Then half. Then this is going to give me 36 left-hand side, and then half of 10 is 5. So I have 5x squared. And then half of 2 is 1. So I have plus y squared. Okay. Then now I can say this is my equation number 2. Right. So let's say this is my equation number 2. Now, from equation 1 and equation number 2, I can say, let me substitute equation 1 into equation 2. So what's the meaning of that? Where there is y, I will have to substitute by this whole expression here. So note this. I will have to substitute by this whole expression. So where there is y, I will substitute by this whole expression. So note that there I have y squared. So I have to put that whole expression in and then square it. So I have 36 is equals to 5x squared plus in bracket 6 minus 5x and then square, which I have to expand this. So 36 is equals to 5x squared. And then if I expand here, this is going to be 36. And then do your maths there. 6 multiplied by 5 multiplied by 2. That's supposed to be negative 60x, and then this is supposed to be 25x squared. So if you fall there and do your maths, you end up with that. Now here, the 36 and the 36 is supposed to fall off. 5x squared plus 25x squared is supposed to be. So let's say we have 0 here, and then we have 30x squared, and then minus 60x. Whoa, interesting. Then if we divide both sides by 30, let's say dividing both sides by 30, then obviously we still have our 0 here. If we divide this by 30, we have x squared only. Divide that by 30, we have minus 2x. Interesting. Then continuing with this, we have a common factor of x. So this is x bracket x minus 2 is equals to 0. And then now let's take this over here. So my x can either be 0 meters per second, which means this can be brought to rest after it meets with that, or my x, so let me say or, x can be 2 meters per second, which means from here might be quite impossible because after collision, we are expecting obviously for this to either increase or decrease. So it cannot remain the same. The velocity cannot still remain 2 meters per second after the collision. So that means this one here would have to be incorrect. This one would have to represent the initial velocity. So, okay, this one, we won't take it 2 meters per second. So we're only going to run with 0 meters per second. So our assumption is that after the collision, it was brought to rest. After it collided with a block y, it came to rest, or the 2 kg block, it came to rest. Now, since we are only considering where x is equals to 0, let's calculate y. So y, if x is equals to 0, we would have to choose any equation here, whether 1 or 2. But then since equation 1 is already in y being the subject of the formula, we can just say 6 minus 5 and then multiplied by 0. So our y will become 6 meters per second, which it makes sense. It means that after it collided, then y had an increased velocity, right? So after the collision took place, that means after it brought this to rest, then we saw that there was an increase in velocity of that one. Okay, and then, or maybe if we can say y is equals to 6, and then let's check if our x is equals to 2. So we have 5 and then multiplied by 2. Then this is y is equals to 6 multiplied by 5 times 2. Then this is giving us negative 4 meters per second, which again, if we can check that, it does not make any sense, right? It does not make any sense. Because now it cannot be the same velocity. So which is why we discarded the 2. So, okay, let's deal away with the 2 and the negative 4 here. So that only leaves us with x being 0 meters per second, which means it was brought to rest. And then this here being 6 meters per second, to which direction now? East. So that means it rebounded with the 10 kg block and then gained velocity. Now it makes sense because the 10 kg is a heavier object. So when it comes here, it bounces off from the 10 kg and bounces off with a greater velocity of 6 meters per second. But then during that collision, the 10 kg block is brought to rest. So that's basically what happened here. So it was a very nice 7-mark question right there. So pretty worth it to solve it using your simultaneous equation. We know with 6-mark, 7-mark questions, and then whereby you have 2 unknowns, it is most likely that you would have to use simultaneous equation. So, okay, let me know how you tackle this one on your own. Or maybe if it shired you, let me know as well, and if you do understand. But then with all that being said, please press the thumbs up button, share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.